All right, line A4, learning task 1, we're going to take a look at describing series RL, that's going to be resistive and inductive types of circuits. Now, a lot of what we are going to go and cover inside of this learning task is going to seem very familiar to you. We just went through learning task A1, and that whole module A1 just had a pile of stuff to do with our base theory. What is an inductor, what is a capacitor, and how are those things utilized inside of a circuit. What we're going to do now is we're going to examine them together as a series component, meaning that we are going to go and have some inductance, draw an iron core inductor, in line with some resistance. We don't do a ton of series circuits as an electrician. It's just not, how we like to go and place a lot of stuff, because it's all going to be dependent then, and then, if we have a failure on one device, it's going to take out the entire circuit. However, we have got a lot of components that are going to go and have series inductive types of characteristics, particularly anything that's going to be wire wound, motors, transformers, ballast, anything that has got windings of wire and has got the physical wire inside of it is going to go and have this series type of circuit. So the theory that we're going to cover over here is going to go and show up again later on once we start getting into complex RLC types of circuits, because we're going to examine motors as being series RL circuits in particular for this year. All right, let's take a look and just talk about resistance and resistance of load. We've gone over this graph a number of times, but we know that anytime that we have got voltage over top of just a resistance, that we are going to go and have current flow that is going to go and peak at the same time and drop away. We know I is equal to E over top of my R that I'm going to go and have, which would mean that when I've got 0 volts, I would have 0 amps when I've got a resistive type of circuit. So we see that we get 0 and 0. We see that when we get peak voltage, we get peak current, etc. We also see that if we go and take our volts and our current and multiply them together, we're going to go and get a power waveform. And we see something that's very critical for our understanding of this whole next module, which is that all of my power is going to be in what we term as being the positive, or the useful type of section that we're going to have over here. Whether I've got positive voltage and current, or whether I've got negative voltage and current, because a negative times a negative equals a positive, we see that our power waveform is always going to be up there. If we wanted to go and graph them out, we could graph them out either side by side or superimposed. Because we have got a series type of circuit that we're going to be looking at, we're always going to reference everything onto our current. Current has closed arrowheads. We see that our voltage and our current are seen as being in phase. In other words, they operate at the same angle, which is how we differentiate when something is going to be in phase. When we talked about inductances, everything starts to look a little bit different. We know that the property of inductance is any type of a circuit that is going to go and oppose a change in current. Remember that it is going to always be that change in current that is going to go and be opposing. They do say another way in your binder as well. They say that a circuit that has inductance has the ability to go and store electrical energy in an electromagnetic field. We talked about that when we were covering these, that the energy that's going to be stored would always be in that electromagnetic field if it were in DC. However, once we went into AC, we saw that we had that continuously changing waveform, the AC voltage waveform. Therefore, we were going to have a continuously changing amount of current that was going to go and happen as well. We know that anytime that we've got a circuit that has only got inductance, and this is a purely theoretical inductor that we have over here, but if I were to have a purely theoretical inductor, I would go and have counter EMF that I would generate off of it, which would be the only thing that I would have in opposition, right? Kirchhoff's law of voltage, the sum of all source voltage, is going to be equal to my drops that I'm going to have around the circuit. So I'm going to have, and it doesn't show it inside of here, but I'm going to have another waveform like this that's going to be my counter EMF. And we know that the formula for counter EMF is that E is equal to negative L delta I over top of delta T, that we would go and see off of that. Because we already know that formula over there, we can therefore say that, look, the inductor stays the same the whole time, therefore that L value is going to go and stay the same. I'm going to draw a little box around that just to symbolize that we've got a locked down value. Time never changes. Therefore, the only thing that could be changing for me to go and get large values of counter EMF would be that my current would have to be going through maximum rate of change. And we see that over here, that when my current is going through a maximum rate of change, I'm going to go and have maximum counter EMF. Once again, when my current is going through a maximum rate of change, I'm going to go and have maximum counter EMF off of this one here as well. Ultimately, all that we took a look at in our first module, A1 there, and with this whole counter EMF, led us to this other formula that we have that's defined inside of inductance. That's going to be my inductive reactance, or my opposition to current flow caused by my inductance is going to be equal to 2 pi FL that I'm going to go and have. In other words, if I have got a higher frequency, I'm going to have more inductive reactance. If I've got a higher inductance value in henries themselves, I'm going to once again have a greater amount of inductive reactance that I'm going to have off of this. All of this is going to be related together through that formula. This is just for now something that we are going to go and keep memorized. We're going to come back to this formula later on once we start taking a look at inductors and capacitors together inside the same circuit. But for now, just know that this is the formula that we will use to calculate the amount of inductive reactance. Once we know the amount of inductance reactance based upon these, we can also calculate the current that I would have inside of that circuit. And the current is simply just going to be my V that I'm going to have over top of my inductor, divided by my XL, the resistance, the inductive reactance that I'm going to go and have of that inductor. If we wanted to go and put this together as a vector, we would go and do so like this. Now, once again, we are going to go and start with current as a reference because we're going to be dealing with a series circuit, which means that current is always going to be the one thing that will stay the same inside of a circuit. So we take a look at our current. We place our current along the 0 axis, which is where our references always are going to be, 0 degree reference over here. And then I just go and say that anytime I've got an inductor, my current is lagging the voltage by 90 degrees. Remember that whole thing about E line. The voltage leads the current for an inductive type of a circuit. So we graph it out so it's going to go and look like this. Once again, this is all just review. The deeper, science of how it all happens, we covered that earlier on this year. Last of all, for review over here, if we take a look at our power that we would have off of a purely inductive circuit, because that purely inductive circuit has got that lagging current, right? Here's where my current crosses, here's where my voltage is, it's 90 degrees out of phase. I'm going to go and get a power waveform that is going to be a useless type of power for a lot of what we deal with. We call this our quadrature power, or wattless power, or VARs. And what it is we are going to go and have a power that's going to be negative for part of our time, negative current, positive voltage gives me a negative power. Then it's going to go positive current, positive voltage, therefore I got a positive power. Goes back to negative, it's got a negative voltage and a positive current, therefore it's a negative. And then over here I got a negative current, negative voltage, and it goes back to being a positive value. And this is that whole analogy of, putting in a deposit and taking the money right back out again. It's useless power to our circuit. It does take a little bit of energy to go and set up. Once again, this is a stabilized circuit. There would have been, a few more wobbles to bring this thing in line at the very beginning when we initially powered this thing up. But this is going to go and be what we refer to as our quadrature power. This is going to be our used power. This is where we are delivering current back to the source. This is where we are taking current from the source. What we're going to do now is we're going to combine this, our purely theoretical inductance, along with this, our purely practical resistance, and we're going to put them together into a series circuit. And over here, they're giving us a series circuit that has got a number of values already laid out for us. The first value that we see is that we have got current and voltage, line current and line voltage. Now, I'm going to go and have to pick a reference for this. My reference that I'm going to use anytime that I'm trying to solve triangles for these, and we are going to go back into the triangles on these, is always going to be my current when I'm looking at a series circuit, because that 4 amps travels through the supply, through the inductor, through the resistor, through the ammeter, back to the supply. It's the one thing that is going to stay constant throughout this circuit. I can use that 4 amps as well to go and develop values of voltage that I'm going to go and have across my components, as well as I can go and use it to develop power. We can also develop another triangle that's going to be my impedance triangle. However, we're going to be very, very careful with my impedance triangle. We do not want to rely on the impedance triangle because it only really works well for us in series circuits. The one triangle that is always going to work for us all the time, everywhere, is going to be the power triangle. So we're going to lean heavily on our power triangle. Okay, let's start by developing our values of voltage. Voltage is equal to my current times my resistance. Now that's my simple Ohm's law. If I go and take a look at this, my resistance isn't resistance, it's reactance, but I can go and use the same format. I can say that my VL is going to be equal to my IL, the current through the inductor, multiplied by my XL, the opposition of that. This one over here is going to be my current through the resistor, my resistance of that. If I take 4 and I multiply it by 24, I would find out that I'm going to be dropping a value of 96 volts across here. Actually, why don't I just drop that V equals 96 volts. If I take a look at this one over here, I've got 18 ohms and I have got 4 amps. 18 times 4 is going to go and get me to a value of V 72 volts. And here's where we start to run into issues, is if we're not very careful about how we add stuff together vectorially, we can run ourselves into problems where we say, well, 96 plus 72 equals a grand total of 168 volts, which we would say, well, that does not go and line up with this 120 volts. Well, absolutely, it does not line up when I look at these as being just straight numbers. What we have to do is we have to remember that anytime we have got resistance, that resistance is going to be at an angle of 0. Anytime that I've got inductance or capacitance, it's going to be at an angle of positive 90 or negative 90 that we would be dealing with for those. What we have to do is we have to go and add these things vectorially. Now, anytime that we are going to be working in these things for inductance, if we take a look at our voltage across an inductor, we know that the voltage across an inductor has to go and lead, right, by 90 degrees. We saw that, over here. My voltage for the inductor is at 90 degrees, and we saw that my voltage for a resistance was going to be at 0 degrees. So when it comes to this circuit over here, what we'll want to do is we're going to want to go and add this voltage over here at 0 degrees, angle 0, and this voltage over here is going to be at an angle 90 that we're going to have. Your book is going to do things a little bit different. They're going to go into Pythagoras, they're going to go into cosine and sine and things like that, throw out a bunch of these. In most cases, I'm going to go and bypass all of that, and I'm going to jump straight into the capabilities of my calculator. Because the calculator can do this math so simply, why not? Why would we, screw around with trying to make things more complicated than they need to go and be? Let's go and pull up that calculator right now, and we will do these calculations. Here's my calculator. I'm going to go and place in the values 96 at angle 0 and 72 at angle 90. So I'm going to go 96. Oops, sorry, I got to put it in the right mode here. Mode 3. Your calculator will remember. Mine always changes out because it's a virtual one here. I've got it in polar mode over here, so now it's going to be 96 angle 0 plus 72 angle 90. And when I punch that in, it brings me out to a value of 120, and I can find out the angle of this thing at 36.87 degrees. So I can go and draw out this triangle that we have over here, and I get the same values just by me punching them in on the calculator. That's what we just did over there. We see we're at 120 volts. That makes sense. I mean, sum of all voltages equals our source voltage over here. And we've got an angular displacement of 36.87 degrees that we are going to go and have off of here. This gives me my values of voltage that I'm going to go and see around here. Now, because we're in a series circuit, we do have voltage drops. If this was a parallel circuit, we would not be able to use a voltage triangle. We would have to go and use a different triangle. We'll cover that one later on. But for now, we're going to work inside of this voltage triangle. The beautiful thing about any circuit is all the triangles are going to be the same shape, meaning that they're going to go and have the same degrees that we're going to go and have off of them as well. I can develop from this, I can develop another triangle, one that we are going to go and use carefully. And this other triangle that we're going to look at is going to be the one that's going to be labeled as being our impedance. It's where we're going to take a look at our resistance and our inductance. And we're going to graph them on the same sides as what we had before. In other words, I could go and take my resistance in watts are always on the 0 axis, and I can graph them against my inductance, which is going to be at 90 degrees up because we are once again following this same format over here. My voltage for the inductor is up there, therefore my inductor values are going to be up there as well. Once again, taking my calculator, I could go and punch in for my impedance. So 24 at angle 0 plus 18 angle 90 equals a value of 30 at 36.87. I see it's the same angular degrees, therefore that's probably going to be fine. It is fine. And I've got 30 ohms of resistance that I'm going to have off of here. Alternatively, you could have also found your total impedance by taking a look at what does the source itself actually go and see. Remember, the source has got no eyeballs. It has no clue what's downstream. All it knows is that it's got 120 volts, 4 amps, and I know that R is equal to E over I. If I'm taking a look at a source, I know that I don't have R. Instead, I've got Z, the total impedance. It doesn't know what's all going to be downstream of this because, once again, has no eyeballs. All it knows is that's feeding power out, and when it feeds that power out, it sees that's 4 amps and 120 volts. So you could do the same thing to get your impedance over here. We'll change this now to a Z because we're looking for impedance. Take 120 volts, divide it by my 4 amps. Would also get you to 30 ohms that we would have. We saw that off of this one over here as well. The last thing that we're going to go and take a look at is going to go and be the power that we would have out of this circuit. Now, the power is going to be very, very important to us because power never lies. Power never lies. The other values don't lie to us so much, voltage and current, but it's easy to get them confused. Whereas if I'm dealing with power, it doesn't matter if I'm going to be in a series circuit, a parallel circuit, a resistive circuit, an inductive circuit, a capacitive circuit. As long as I take everything back to the power values, I can add my values together straight up. And this is going to become super, super handy to us later on. So make sure that you, as much as possible, try to work inside of power. I'm going to show you other methods that we can get to the same one. They're just mathematical proofs. But by and large, I want to stick with the power itself. What is our power for this one? Well, if we go back to the actual circuit itself, I'll just erase all of that whiting out that I did. There's a bunch of things that we could do to figure out what our power would be. One of the easiest things to figure out what our power is going to be would be for me to go and use the formulas that are going to be I squared R. I could take that current and I could stick it through this resistance, I could stick it through this reactance, I could stick it through that impedance, and that would give me all of my values of power. Or if I've already got my total amount of VA, volts amperes, 120 volts and 4 amps, I could put it in at the proper phase angle, and then I could just get the calculator to go and do the rest for me. That's exactly what we're going to go and do over here. I know what my VA is, my apparent power that I'm going to go and have over here, because my apparent power is going to be made up of my line voltage, 120 volts, multiplied by my line current, 4 amps, that I'm going to go and have over here. Which means that I've got a total VA of 480. 480 VA. What I can do, because we know all these triangles are the same, is I can punch this in and put it in at 36.87 degrees. And when I do that, it's going to automatically spit out my bars and my watts for me. I'm going to just go ahead and do that because it's the easiest method for solving these ones, and why not? I'm here, by the way, to teach you electrical theory, not to show off in trig. Okay, the book does enough showing off in trig. I don't know who wrote this, but it was somebody that just had intense love for trigonometry and cosine and angles and Pythagoras, etc. What we are required by the ITA to do for what you're going to cover inside of here is to describe the interaction and describe how to get the values. I don't need to go through the whole trig method because you're going to be using this calculator on your exam. We're going to go and use this calculator for what we're doing now. For those of you that are still working off your TI-83, get the proper calculator. You just spend the couple of dollars over at Staples. Make sure you got the proper one. Talk to another apprentice that's finished through. They probably have one that they don't use anymore, but make sure you're working off of this one. Okay, 480 at angle 36.87. I know we've rounded it a little bit. And then I'm just going to hit equals. And all that does is that stores this number in memory for me. So now it's 480, and I can go over to here, and it tells me it's an angle 36.87. And I can go back, it tells me the magnitude. What I'm going to do now is I'm going to do an XY conversion. So I'm going to convert to XY. What that does is that kicks out my X value first, 384, and then it kicks out my Y value, positive 288, that I'm going to go and have. It's fantastic. I see this as the Y value because I got that little I or J operator, and I see it's a positive value that I'm going to have over there. So 384, 288 is what I'm going to have for this one. I'll just drop those numbers right in here. 384, 288. You can verify that inside of your book. In your book, they go through and do the I squared R for all of them, for my true power, for my VARs, etc. They go through a bunch of different methods to go and solve to get each of those individual values. All of them are just as legit. However, they're not all necessary to go through. This is why I'm choosing to go and utilize the power of the calculator to go and spit those values out for me instantly. This is going to go and now lead us to our final section that we are going to have to take a look at, which is going to be where I am going to now deal with what is referred to as my power factor. Power factor is going to be a ratio of my real, the useful power, compared to my VA, the total amount of power that I'm going to be taking in. In other words, for the amount of volts and current heading into the system, how much am I being able to go and take back out? Because I'm losing a little bit to this. So for me, this one over here, I'm going to go and take 384 divided by 480. VA watts. 384 over top of 480. When you go and do so, oh, that's 348. 384 gets me to a power factor of 80% that I'm going to go and have off of this one. It's an 80% power factor. The other cool thing that we can do to get to a power factor is we know that power factor is going to be my watts over top of my VA, which is going to be the cosine of my angle. So I can go and take the inverse cosine of my angle to go and get my power factor. Power factor equals cos to the -1 of my angle that I'm going to go and have. Let's punch that in as well, just to go and verify that. So we are going to go and take the inverse cosine of bracket, my angle 36.87. Oh, sorry, cosine 36.87. I meant to do the cosine one there. Power factor is cosine of the angle. Going back into this one here, I wrote that one wrong, my bad. Cosine of the angle over here, the power factor is going to be cosine of angle theta. The inverse cosine of theta is going to be able to kick us back through there. We'll deal with the proper one later on. But we see that the cosine of our angle that we kicked out gave us this power factor here. Okay, the very last thing that they show inside of the module over here is the fact that all three of these triangles are going to go and be similar. They're going to go and have the same ratio of sides that we are going to go and have. There's a couple things that I want to point out about them though. First of all, the voltage and impedance, we're only going to be able to go and use those if we have got a series type of circuit. The power triangle we can use on all types of circuit. There's nothing wrong with using volts and impedance, if that's the way that you prefer to calculate through, provided you do so accurately and you watch which type of circuit you're operating inside of. If you take it outside of one of these types, then you're going to always run into issues. If you try and take this into either a compound circuit or if you take it into a parallel, these triangles over here will not work for you. Okay, power factor is going to be examined much more in depth later on once we start looking at power factor correction. BC Hydro does go and mandate that we got to maintain a 90% power factor, and if we have a maintained power factor, not instantaneous, but a maintained overall power factor that is going to be below that 90% power factor, they are going to go and bill, and they go and put on some massive surcharges based upon the types of rates that you're going to have. For an example, I had a customer back when I was running my own company who had at the very far end of, he had a very large property, he had a small shed at the very far end that he had a pile of deep well pumps inside of there. It was a whole pile of irrigation that he had. And they were run off of a high voltage transformer. So he had a transformer inside of there over the winter. He kept the transformers energized. So they were just magnetizing. There was just inductive power being used. He kept the transformers energized so that he could go and utilize 120 volt supply for an alarm system, just due to problems he'd had with break-ins inside of there. Because it was off of a special type of service called a seasonal or irrigation service, and because he was almost strictly going to be dealing with his VARs that he had at that point, his watts that he had over the winter worked out to be about maybe $3-4 in watts. But because he was so heavily into the lagging power factor, it was almost all VARs with very little watts, he ended up with a bill. When they started that service back up again, he had a $3,000 bill for the power just to go and run one of those tiny little wall warts for his alarm system inside of there. Nothing he could do about it either, because he had, contacted an alarm company. They'd put it in. We weren't involved in the install or anything like that. He just had me go over the bill because he didn't understand where he was getting that massive charge from. Okay, the last section inside of this one is going to talk about the resistance of an inductor and how we actually deal with inductors themselves in a practical application. Oops, sorry, let me go down to my drawing over here. Practically speaking, every inductor is going to go and contain these two values. We're going to go and see resistance, which is going to be made up of the copper that the turns are made up of. We're going to go and see inductance, which is going to be based upon L, right? L is going to be equal to my N squared mu A all over top of little l. And then my R is going to be equal to my K times L over top of my CMA. Oops, CMM, that's CMA that I'm going to go and have. That's going to be unable to be separated for all of our inductors. So what we can do is we can go and form a ratio off of them. Now, if I've got an inductor, this resistance, I would measure as DC. This resistance is going to go up with my shred loss, the skin effects, hysteresis, radiation, eddy current, and dielectric. Those are all going to go and add on to that resistance. So if you measure this thing cold with just a DC ohm meter, you can expect that it will be a little bit larger once you actually power this thing up. And in a lot of cases, commercial inductors are going to go and have what's my figure of merit, or Q, that we are going to go and use for that. We use Q for all sorts of stuff. But if I have got a coil that has got a Q, it's just going to go and talk about my XL, the ratio of my inductive reactance compared to my R. Because if I'm buying an inductor, I'm buying it clearly for its inductance. I don't want to have a lot of resistance. I want to have maximum inductance out of it. So XL over top of R is going to go and give me that value of Q that we would see out of these. Q, by the way, is going to be a tangential factor. If you take a look, if I've got a Q of a coil, it's really going to be telling me my XL over top of my R, so it's going to be telling me the tangent of that angle. If I take the inverse tangent of by Q, it's going to go and spit back out the angle that I would have as well. All right, that covers us off for Series RL. Let's move on to Series RC.